Okay, so let's start. So I'm going to confine now to SU2 group. SU2 group is by now you should all know the usual notation of group notation. S denotes the group element should have determinant +1. U is for the unitary groups. 2 is to denote the first lowest non-trivial dimension of the representation of the vector space is 2-dimensional. Okay, the corresponding matrices will be 2 cross 2 matrices, and the number of constraints, if you subtract 2 cross 2 matrices, unitary matrices, means it should satisfy unitarity condition and determinant equal to 1. So you will get the number of parameters, which is number of real elements in the matrix. Okay, so there are only 3. That is why you have theta vector is formally written to remember that there are 3 components, theta 1, theta 2, theta 3. Okay. So u of theta this is for SU2 group. Once it is a group, I try and put it to be capital S, capital U, and 2. So this will have an exponential form. It will be an exponential form I by H cross theta dot the generators. I said no, number of parameters will always be equal to the number of generators. In the case of rotation, I wrote it as orbital angular momentum. Here I am going to write it as a total angular momentum, which includes spin angular momentum and orbital angular momentum of a particle. Okay, so this will be your general element, where J's are the generators. This cap is generally written for a linear operator, or you can even write the matrix representations for it, depending on which vector space it is going to operate. Okay. So this is a familiar algebra of the generators. Algebra is denoted by small s, small u and 2. Okay. This is SU2 Lie algebra. So how do you define this explicitly? The way to see it is that you could take multiply 2 such matrices. Okay, I am not going to do this for you. Take 2 such matrices. Okay. What does the group property require? If you take a product of 2 such matrices, it should again be an SU2 matrix, but the parameters are not just going to be additive. When will it be additive? If you do a rotation about an axis which is the same, then you can add it up. Okay. But if you do rotation about theta 1 vector which is in a different direction and theta 2 vector in a different direction, it will give you again a unitary matrix which depends on phi. Okay, this is also a vector, but it will depend on theta 1 and theta. Okay, it will be from what exact functional form I will not know, but depending on what is the value I can find it. Okay. So use the infinitesimal piece and keep up to order theta 1, theta 2 and see what you get, and you will end up getting this algebra for the generator. Just like I did for the orbital angular momentum, you can do this for this case. Okay. You see that the dimensionality of the vector space depends on 2j plus 1 dimensional vector space. So I said that j hat is 2j plus 1 cross 2j plus 1 matrix acting on vector space which is given formally as, you all know this, you write it as J and M. We'll come back to why we add two numbers here, but this M value, so this M takes values from minus J plus 1 up to J. So there are 2J plus 1 states on which this 2J plus 1 cross 2J plus 1 matrix acts. You all know this. So those are, if J is half, which is your lowest two-dimensional vector space, which is up spin and down spin. So someone interestingly pointed it out that in your discrete groups, the character tables tells you that you have only up to certain dimension irreducible representations, right? So like if you take a tetrahedral group, you cannot get a 5-dimensional irreducible representation. In the case of continuous groups, for high J, you still get a irreducible representation, but that irreducible representation acts on the corresponding vector. There is no limit to, there is no analog of character table here, but we will see how to get irreducible representation. Just because I write a 3 cross 3 matrix, it need not be an irreducible. You can always, if you are able to find a matrix with block diagonals, then it's not an irreducible. But analog of the character table, you can allow all possible dimension irreducible representations for the continuous. Okay, so why are we using this state is something which you have learnt in quantum mechanics. That is what is called as a Casimir operator. What is a Casimir operator? Casimir is bilinear in generators, okay, and it should commute with all the generators of the Lie group. So for example, this J dot J is bilinear in generators, right? I can write it as J1 squared plus J2 squared plus J3 squared, and J dot J you can see with any of the Ji's, it is 0 for all i's. Okay. So this tells you that you can write a state which is a simultaneous eigenstate of J dot J as well as any one of the J's. The reason why any one of the J's is because amongst the J1, J2, J3, the commutator is non-zero. So you cannot simultaneously diagonalize J1 as well as J2 or J3. One of them can be simultaneously diagonalized with this one. In all the quantum mechanics textbooks, we use a choice which we call it as JZ, which is, this is just a choice. You can write a new book or a new, set of notations where you can call Jx to be your axis where this is happening, but usually we are following, even in spherical coordinates, Z to be the axis which, and we choose the Jz eigenvalues to be M, right? What I mean by this is that Jz on Jm will be Mh cross Jm, okay, is that right? And J dot J on Jm, you can find the number, but if you find it explicitly, it turns out to be this. Both are eigenvalue equations, but if you do Jx on Jm, it is not proportional to Jm. Similarly, Jy. is not proportional to Jn. Is that clear? Because of this property and my choice that we are going to take Jz to be simultaneously commuting with J dot J. So this convention which we write, Jm is a simultaneous eigenstate of a Casimir operator. This is what we call it as a Casimir operator. Casimir operator is one which commutes with all the generators of the group. I am confining to SU2 group. SU2 group have J1, J2, J3 as the generators. Casimir operator will commute with all the, and Casimir is constructed using bilinears of the generators. And then we make a choice and write those states which are simultaneous eigenvalue equations. So simultaneous eigenstates of this as well as this. Okay. In fact, using this you can also see the matrix representation of it for every j. This I constructed it for j equal to half by showing that it is 1 and minus 1. If you take j equal to 1, you can construct what is the matrix for it. Okay. So if you want to find Jz, which is a 3 cross 3 matrix, then you can rewrite it as right, because it's an eigenvalue equation. If m is j, it will give you plus 1. If, of course, I have suppressed the h cross, if you want I can put the h cross. And if m is 0, so m is running from minus j to plus j. So if m is j, it is 1, m is 0, it is 0, m is minus j, it gives you a minus 1 for j equal to, this corresponds to j equal to 1. Okay. So some of the notations, j equal to 1 is 2j plus 1 dimensional matrices. Okay. So the degree of the matrix is 2j plus 1. So j equal to 1, this will be 3-dimensional matrices for jx, jy and jz. Okay. Is that clear? Similarly, using these you can see it is off diagonal and you can work out what are those off diagonal matrices for every representation. You don't need to. Every representation, I mean different j's corresponds to different representations. Just like any reps, 2-dimensionally rep, 3-dimensionally rep. So each one is 2j plus 1 dimensionally rep. And for different representations, you can use these equations to construct the matrix representation. Is that clear? So bilinear in generators. Bilinear means product of two linear operators. Take a product of 2 linear operators, quadratic. This is the quadratic Casimir. Yeah. Is that clear? For example, J dot J. In every group, you will have a set of matrices, matrix representations for the generators, which will be diagonal. Okay. So, if you go to SU3 for example, I want to construct the generators with certain properties for unitary group, special unitary group. What is the properties? It has to be traceless and Hermitian. This is traceless and diagonal also. If I go to SU3, so for SU2 if I am going to do only with the lowest non-trivial dimension. For SU3, the lowest non-trivial dimension is 3 cross 3 matrix. So there you can allow one more diagonal matrix, which is traceless. Is that right? So if I write the diagonal matrices, so SU3, how many generators are there? SU3, number of parameters, real parameters is 8, number of generators is 8, and I am going to denote it as lambda 1, lambda 2 up to lambda 8. Just like J1, J2, J3, you will have 8 such matrices. Any element G belonging to SU3 will be rewritable as exponential of I by H cross phi, which is 8 of them. Okay, so I am going to put phi I, lambda I hat, summation over I going from 1 to 8. Are you all with me? That's the model. These are the SU3 matrices, which involves 8 generators, and there will be an algebra between the 8 generators. What will the algebra be? It will be some lambda I with lambda j should give me some structure constant. Okay, so this is the SU3 algebra. Okay. Okay, this is the group element, which is an exponentials of the generators, and there are 8 parameters and 8 generators, and the lowest non-trivial dimension has to be dictated by this. Okay, so you can write lambda hat, the lowest one, just like we wrote for SU2 as poly matrices. Here you have a set of matrices which are 3 cross 3 matrices. Okay, lambda i's are 3 cross 3, and the aim is to find traceless Hermitian matrices. 3 cross 3, which is traceless, whatever you write here, you understand what I am saying, right? The generators have to be traceless and Hermitian, and from there you found that the number of parameters will be 9, and then you traceless and Hermitian will have number of parameters 8, right? So it is 1, 2 which are real, then these are complex conjugates, so this is 2, 4, 6, 8. Complex numbers have 2, but this element is it's not independent. So 2 reals A, B, Z1, Z2, Z3 are the independent parameters required to specify a traceless Hermitian matrix. So they are 8 number of real elements. These are complex. So 6, 7, 8. Okay, is that clear? So 8 real elements. That's why 8 parameters. Now I want to construct the analog of Jz, which I did for SU2. The poly matrix sigma z was diagonal. How many diagonal matrices I can construct for the lowest non-trivial representation of SU3? So tell me, how many are possible? First of all, inside SU3, SU2 will be a subgroup. Okay, that's something which you should know, that any element of SU3, you could write the elements which is, so SU2 is definitely a subgroup of SU3. Okay. So, the conventional generator which you have for sigma z, which was plus 1, 0, 0, minus 1, this should sit inside the SU3 generator as one diagonal generator. So, let me call the generator for conventional reason just like we call that as J3. So, lambda 3 should be a 3 cross 3 matrix for SU3. So, this is an element of SU2 algebra. So, this 3 cross 3 will be 1. Okay. So, this one is an element of SU3. This is traceless and Hermitian.